Welcome back to Air Quality Matters. We already have the tools and knowledge we need to make a difference to the quality of the air we breathe in our built environment. The conversations we have and how we share what we know is the key to our success. I'm Simon Jones, and coming up, a conversation with John Wenger, Professor of Physical Chemistry at University College Cork. Strap in, folks. We're talking about hydroxyl radicals. Yeah, I know, I didn't have a clue either. But it turns out these little things are one of the engine rooms of our environment, have a massive impact on our air chemistry that makes a lot of the pollution that we talk about on this show, and very tricky to measure, in the parts per trillion and not around for very long. But John and an international team have been doing some amazing work over the last few years looking at just this, have state-of-the-art atmospheric labs down here in Cork where we're recording today, and who doesn't love a bit of air chemistry? I've known John since he chaired the Ventilation Advisory Group, which I served on during the pandemic here in Ireland, and was really looking forward to catching up with him post-COVID to chat about this, the Radical project, and air pollution in general. Lucky enough to be recorded here in the Great Hall in UCC, University College Cork, I really hope you enjoy this one. Please don't forget to check out the sponsors in the show notes and at airqualitymatters.net. This is a conversation with John Wenger. There were kind of three areas we were going to have a look at today. One was about free radicals and atmospheric chemistry in general, I think, and your labs and what you're doing here. Stuff on ambient air pollution. Oh, what happened with that contract, by the way, the Queen's jobby? Do we know, are you part of that? Has it been awarded? Or?
It's been reviewed.
Okay.
But we were the only consortium that was going for it, because you have to have a big inclusive consortium. And so we worked hard to get what we thought was a good consortium together that included the relevant academic institutions, the relevant bodies, north and south, county councils, all the rest of it. So it's got a big consortium, but we're the only one going in, so I expect we'll get funding for it.
Yeah, it's just it's in the review phase, is it? No.
Yeah. So this is a program called Peace Plus, and the issue there is related to the second part, which is it's really driven by the solid fuel burning issue.
Yeah.
Okay, that the legislation is different north and south, and essentially cheaper coal from Northern Ireland can be brought into the Republic.
Yeah.
But it doesn't have the same standard, right? So they were looking to, in the end, they're looking for ways to change the legislation in the North, but they don't have an information basis to do it because there's no research at all on the sources.
And how big's the issue with agricultural driven PMs? Because that's one of the things that I only copped. You know, it's amazing how much you realise you don't know. Every time you go to various things and somebody goes, well, of course, we're looking at agricultural particulate matter. And I'm going, agricultural what now? And so, and from recollection, that was methane and other gases from agriculture creating air chemistry and particulates.
I mean, the chemistry for methane is extremely slow. It's a greenhouse gas, so it doesn't really react very well with the hydroxyl radical. It's too slow to act on a local basis. It will only undergo, it moves around the world, all right? It moves around the planet before it eventually gets degraded. That's why it's got such a long lifetime. So it's very slow to react. And what we have, though, from agricultural emissions is ammonia, right? That's the key.
Ammonia, that's it,
That's the key thing, all right? So the ammonia in the gas phase can dissolve in water, but also it combines with acidic gases like sulfuric acid, nitric acid. So any NOx species, you've heard of NOx or SO2, eventually gets oxidized into the acids. And then you get an acid-base reaction, some simple chemistry, forming a salt. Acid plus base gives you a salt. You might remember that from leaving cert chemistry or O-level chemistry, whatever you did. And this is a source of particulates. So this is stuff emitted as a gas, but then forms particles in the air. So it's secondary PM 2.5. And so when you see ammonium in particulate matter, you've got a good trace back to the agricultural source. All right. So this is omnipresent. Everywhere we go, we see methane. We see ammonium in the particulates. Okay,
Interesting.
So we're linking this now. Slight complication is that there is ammonia emissions in the urban environment as well. So from some of the diesel type vehicles, especially with the AdBlue chemistry, that it's a urea compound, and there may be some ammonia coming from those sources as well in the urban environment. But in the main, it's agriculture. And this secondary particulate matter just means that this elevated background. And we do see some highs in springtime when there's a lot more manure and so on being spread, right? And slurry.
Interesting.
Yeah, because those emissions volatilize and they end up converting into particles.
So it's not, you don't see it in the data that you're looking at. We'll come on to this, but we're digressing immediately, which is always great, John. You're not seeing that, it's not kind of event driven in the same way we might see PM events of cold nights and coal fires and things like that. When you're looking at ammonia driven particulate matter, are you able to spot what's driving it?
There is some seasonality to it.
Okay.
But in the end, it is all year round, all right?
Yeah.
Because you do have the animals are living all year round, right? So those emissions do occur all year round, but they're heightened during the slurry or manure spreading season. So when you put that stuff on the fields, and you live in Ireland, right? So you can get those smells quite often.
I live right next door to it. Yeah, for sure. Yeah. And do we know, does it carry the same risk as some of the other particulate, the heavy metals and the carbon-based particulates? Is there a kind of a direct link to these PMs?
I mean, ammonium sulfate or ammonium nitrate per se wouldn't be anywhere near as toxic to things like pHs from combustion, right?
Yeah.
Or emissions from direct combustion sources. So in that sense, no, but it just does add to the burden of PM 2.5. Right?
Yeah.
So it basically gives us an elevated background. If you were to be on the west coast of Ireland, where the wind's coming in from the Atlantic, you've got very low particulate matter. As you move across eastwards, right, you're picking up all those emissions, and you're going to get higher particulates. Just
compound.
Right.
Yeah.
Right.
Interesting.
And so you can see ammonium more or less everywhere. So there's been extensive studies now across Europe. And ammonia, the gas, because of this, ammonia now, the gas has been included in the new EU Air Quality Directive. Okay, so it's one of these newer species like black carbon.
And is it is it included for its particulate generating potential rather than its direct toxicity?
Yes, by and large.
Interesting.
Right, so it really is about its secondary particle forming ability.
Interesting.
It's the main base in the atmosphere that reacts to the acids.
Yeah.
Right, so all the combustion processes produce NOx, nitrogen oxides, which then can be converted into things like nitric acid. Sulfur dioxide gives you sulfuric acid. They can get incorporated into water droplets, or they can combine with the gases directly, and then you get salts, right?
Yeah.
And these just add to the particle growth, particle mass that's present in the atmosphere, PM 2.5.
Well, let's come back onto PM 2.5,
all right,
because that is question 2. In first instance, I want to understand what the hell a radical is,
right?
In as simple terms as possible. You were generous enough to show me around your labs about a year and a half ago, maybe even 2 years ago now, and it's a phenomenal piece of kit and research, obviously.
Yeah.
And you've been part of a big international project looking at free radicals.
Yeah.
Could you give me the lowdown on what we're talking about here? Because it's certainly the first time I heard of it, and then I think unless you're into ambient air quality or chemistry, this may not be familiar to a lot of people.
Yeah. So I think people would have heard about free radicals in the body, maybe. Okay. In a similar way, there are free radicals in the atmosphere, in the air. Free radicals are just basically very reactive, short-lived chemical species. From a chemistry point of view, they have an unpaired electron, and that electron wants to find another electron, right? And so it means that it's very reactive, wants to make chemical bonds. All right, so it's very reactive. In the body, free radicals can do a nice job of mopping up some pollutants into the body. Too many free radicals can also be a problem, though, right? Because that can lead to some stress situations. In the atmosphere, it turns out that free radicals drive the chemistry of the troposphere, the lower part of the atmosphere, and in particular one called the hydroxyl radical. So this is water, but you remove one of the hydrogens, basically, and you got the hydroxyl radical. And so this is a very short-lived species that is like a gas phase species. It's very reactive, and it's present in extremely small concentrations. The concentrations during the day are something like about 1 in a part per trillion, okay, so a part per trillion level. So 1 radical in a trillion molecules of air. That's 10 to the 12.
Yeah.
So it's tiny. It's way less than the concentration of ozone. It's about a millionth less than the concentration of ozone in air.
I'll have to do my seconds game with that, because when I'm explaining to people the tiny amount of stuff we're talking about with air quality, I do can anybody here tell me what 1 million seconds is?
Right.
You know, and it's like 12 weeks or something.
Right.
And then 1 billion seconds is 32 years. Like, the leap is enormous.
Yeah.
So 1 trillion, I dread to think what we're talking about. Just tiny amounts of it. Yeah.
Tiny amount.
But so if it's so tiny, is it important then? Like, is it driving something in the
because it's so reactive?
Okay.
It's so reactive that even at small concentrations, it just reacts with almost everything. Okay, so the hydroxyl radical will react with NO2 from combustion, sulfur dioxide, react with carbon monoxide. It will react with methane, albeit a bit slowly. It will react with all of the organic compounds that are emitted from man-made sources like combustion, vehicles, wood burning, industrial uses, home care products, as well as natural sources like vegetation, plants, and so on. So all of these species will react with a hydroxyl radical, and they'll undergo oxidation. And it turns out that the hydroxyl radical reacts, but then is regenerated during the day. So there are various cycles, and so it just goes round oxidizing things, because the atmosphere is like an oxidizer. Okay, it's the nitrogen doesn't do very much, but the 21% of oxygen is really key, because once you start the reaction with a radical, you then get oxidation of species. Okay, so for example, when we emit VOCs, volatile organic compounds, from various sources, could be vehicle exhaust, for example, during the day, when the hydroxyl radical is present, I forgot to say that it's only really present during the day because it's produced from sunlight, the action of sunlight on various chemicals, including ozone.
So it's similar to ozone then. It's a kind of a sun-driven thing.
Yep.
Yeah.
And in fact, the hydroxyl radical, while it's made from ozone, it also produces ozone as well, right? So there's various chemical cycles here. The hydroxyl radical can react with an organic compound. We convert NO to NO2. NO2 becomes broken down by sunlight to give you O. O plus O2 gives you O3. And we get radicals being produced which cycle around again.
Yeah.
So when I do my lectures to undergraduates, there is various cycles where you have ozone production from OH, and you get oxidation of volatile organic compounds. So VOCs get converted to ozone, and also the organic compounds can get converted to oxidation products, and some of which have low volatility and make particles. And so these are secondary organic aerosols. And it turns out that these particles from organic reactions contribute to some of the largest uncertainty in climate, our understanding of the climate situation at the moment, okay, because these particles are seeds for clouds. They're cloud condensation nuclei, as they're called. And in addition, they also can be breathed in. They're so small, they're like PM 2.5, and so they have health effects. So understanding this chemistry is crucial for understanding atmospheric composition, understanding ozone formation, and secondary pollutant formation, including particles which affect air quality, health, and climate.
And I'm guessing one of the challenges is because they're so volatile, it makes them incredibly transient. So measuring them and understanding them, while you can understand the chemical reactions, actually testing theories and measuring this stuff, I guess, is pretty complex to do.
Yeah, I mean, the origins of this chemistry go back to the Los Angeles smog. You know, during the 1950s, people were realizing the damage that this smog was doing. Okay, and they figured out that ozone was a key component. Where's this ozone coming from? Ozone is not emitted really. It's always made in the atmosphere.
Yeah.
Through reactions of sunlight, and they've finally worked it out. It's this oxidation of organic compounds initiated by the hydroxyl radical. So it's sunlight plus VOCs, organic compounds, plus nitrogen oxides gives you ozone. And that's the LA smog situation. And that now is happening all around us, not in such extreme cases as the Los Angeles smog all the time.
Yeah.
But this was the real reason why, the state of California led a lot of the legislation on air pollution, right?
So it's a real engine room of chemistry, these free radicals. It's the starting powder for a lot of the stuff that's going on.
Yeah,
interesting.
They really initiate the chemistry of our atmosphere. And as I said, even though they're present in such low concentrations, they drive the chemistry and they control, in a large way, atmospheric composition.
Even though it's so dispersed, even though it's such small amounts, it's potent enough at scale to have an impact.
Yep.
So even though you're looking in the parts per trillion, it when you have a free radical, it's changed and gone. Sunlight's creating that radical in the first instance. That's what you're saying. So it's sunlight breaking down stuff, creating these radicals. One of them being hydroxyl radicals.
Yep.
And it's that's just. Even though it's small, it's everywhere all of the time.
Yep.
Creating
and then
chain reactions.
It gets produced again.
Yeah.
And it kind of disappears at night time. Then another radical called the nitrate radical, NO3, takes over at night. And we know less about that. But it turns out that the chemistry at night time can be important, especially for biogenic VOCs. So VOCs coming from forests and plants and so on.
Yeah.
Turns out to be really quite important for NO3, the nitrate radical.
Yeah, all the kind of the pinene, all of that stuff being generated.
Exactly. And on a global sense, 90% of the VOCs emitted do come from natural sources.
Yeah.
And they have the largest impact on climate. As I said, they become oxidized to give you these organic aerosols, tiny particulates. The haze over a forest is quite well known, this blue haze.
Yeah.
That's secondary organic aerosols. And they scatter light, but they also are the seeds for clouds. And some of that complex chemistry and physics, how these particles interact with water droplets and form clouds, is really behind some of our largest uncertainty in climate models.
So is there a big gap in knowledge here with free radicals? Is that the big challenge is its measurability, understanding its impact, how it changes? Like, what are the questions that are trying to be answered around free radicals at the moment? I mean, we understand they're there. We understand they're reactive. We understand they're the engine room of a lot of complex chemistry. But does it matter? And is it asking questions we don't have the answers to at the moment? Is that kind of where we're at with it?
The detail is in the chemistry, because there's such a large range of volatile organic compounds, and they all react very differently towards the hydroxyl radical. Methane, for example, is extremely slow. You compare methane to alpha-pinene, you said that earlier on. Alpha-pinene is nearly 100,000 times faster to react than methane is. So we find out how fast different species react. We work out some of their oxidation products. We work out which of these products can go on to form the aerosol. So we identify the chemical reaction pathways that lead to aerosols. In the same way, we can look at man-made emissions and look at what happens to wood burning. Do wood burning emissions produce more toxic material as they become chemically processed in air?
Yeah.
Do some of those emissions from vehicles become more toxic or less toxic? And so we follow some of that chemistry. We can do that in the field, but it's extremely complex because there's literally hundreds, if not thousands, of individual organic compounds in air at tiny trace level concentrations. Each of them reacting at different rates, contributing different amounts to the secondary pollution. We can do that, And we can also decide to go into the lab and focus on individual components. For example, study alpha-pinene. For example, study benzene coming from automobiles and focus on one of those chemical pathways. And take alpha-pinene, for example. I would say there's literally 500 studies at least on alpha-pinene, and we still probably haven't fully nailed it. Okay, because the chemistry is so complex. It's very reactive. And once you have one initial reaction, you get several pathways. And then you get several other pathways. And it just
it's like this explosion of branches. Yeah,
you get like an explosion. And so this is where it's incredibly difficult. And taking that information that we generate from the lab and parameterizing it for climate models, for example, is a really big challenge as well. Because it's relevant, right? But we've got to work out how to represent that information in a model, in a real world model.
Yes.
And so that... I'm talking about lab science, I'm talking about the field observations, but then also feeding information into a model as well. And the whole area of atmospheric science now is a combination of laboratory science, field measurement, and modelling. And linking those three is key.
And with radicals and hydroxyl radicals, is it purely about understanding why we're seeing what we're seeing? Or do we consider them a pollutant in their own right, something that we could control or limit the amount of, or do something? Is there some avenues of science that way, or is it just there? It always will be like the sunlight. It's just the engine room it's the secondary stuff we care about, and it's just about understanding that process. Or is there an element of this of trying to understand why we're seeing lots of it at certain times or in certain conditions, and understanding if we can break that chain and limit them in some way that we might stop some of those secondary pollutants?
It's always going to be there, right? I mean, it's natural chemistry. This natural chemistry can get enhanced in more polluted environments. So when we have very polluted, smoggy cities, for example, there are extra gases in the air. That can also be a source of hydroxyl radicals.
Okay.
And so you get faster oxidation chemistry.
Interesting.
You get more chemical processing. And that means it occurs in a shorter time scale, and therefore you get more local pollution.
Okay.
Right? So if the chemical reaction is very quick, that will lead to local pollution. If it's very slow, then the stuff doesn't really react very much, like methane, and it spreads around the world. Stuff of intermediate reactivity has more like a regional impact, a countrywide, or even going across a continent, say. Okay. And so we break down our impact of different emissions into their impact being local, regional, or global. And it's that speed of the chemical reaction which really governs that.
So tell me a little bit about the research that you've been doing and the lab that was set up, and you were part of a big cohort to do this. What was the idea behind that particular body of research?
So for quite some time now, we have been working on laboratory studies using atmospheric simulation chambers. Okay, so the idea here is to recreate the atmosphere as close as you can in the lab. So we have a large facility, which is a room, you can actually walk into it, okay, where we put our vapors and our gases and our particles, okay. We study systems of interest. We might want to look at, say, benzene chemistry. We can add that into our reactor. So the reactor is this vessel, which is transparent. It's a Teflon film, and we have ultraviolet lamps to mimic sunlight so they can generate the radicals. And then we study the chemistry using a wide range of instruments to look at the processes that are going on. We can monitor the different gases, the organic compounds, and also secondary particle formation. So this whole smog formation process in the lab, and originally they were called smog chambers.
Really?
Now we use them for different things, but initially in California, when they were first invented, they were called smog chambers. And the idea, of course, is that when you go to the lab, you can control that environment. And that's the big thing about it, because you can change the concentration of the stuff, right? You can add however amount of nitrogen oxides you want. You can add ammonia gas. You can add existing particles. You can change the light wavelength. You can change the temperature. You can maybe change relative humidity. You've got all of those possibilities in a controlled environment, like an atmospheric simulation chamber that you don't have outside.
Yeah.
Now, what you don't get is the complexity of the atmosphere, but what you do get is the chance to study a system in isolation.
Yeah.
So typically we'd be looking at individual compounds. But people have been playing around a bit more now with real-world emissions, and we've done that ourselves. So, for example, we have done some studies on the chemistry of emissions from little trees. So Sitka spruce, right, is the most widely planted tree in Ireland and the UK, actually, because it grows very well, very quickly. But those emissions, the smell of the forest, they go into the air, right? So we took the vapours that are emitted from some of those trees and put them into a chamber and oxidised whole world emissions from trees. People have done it with car emissions, wood burn emissions.
Yeah.
And so you can do individual studies, individual chemical studies, but also you can do the more complex real world emissions.
So you can see that single pollutant branching out into all sorts of different chemistries you were describing it, right. Or you can introduce more complex soup of chemicals and see. So right. you can do things at different levels and understand right. different outcomes. That's going to be very hard to measure. I mean, that stuff's happening live in real time. Yep. Could be any number of chemicals that are being produced at any one time. How do you even go about measuring that in real time? That's not an easy task.
With very expensive equipment, right? So,
yeah.
I mean, the last 10 to 15 years, I've seen an explosion in online mass spectrometry. Okay, so this allows you to sample the air, whether it's gas or particulate, and get a chemical breakdown of the composition. Okay, and so we've been trying to identify what's in particles, what's in the gas phase, and trying to piece together this complicated chemical picture. It's complicated chemical jigsaw, really.
Speciate particulate matter as well, can it?
Yeah, we can do that as well, right? Okay. So, wow. And there's been a lot of advances the last 10 or 15 years. Now, it is complex, whether you're in the lab as well as the field. You know, if you take alpha pinene, as I said earlier on, the chemistry can explode, and quite quickly you can have 50 different species, some in the gas phase, some in the particle phase, some in both. And getting a handle on that complexity and breaking it down to get something useful, right?
Yeah.
You need the instruments to do that. With these instruments comes a lot of data collection, and with the data collection comes a lot of data analysis. So all of my research team now, and many research teams in atmospheric science around the world, are now writing their own code, writing their own programs to analyze data quickly and efficiently.
I was going to say, like with the chemistry and the amount of data, are we talking obscene amounts of data and computing needed to untangle this stuff?
A full mass spectrum every second, right?
Yeah.
And you know, we've been doing some monitoring just recently now with colleagues from Galway. We've been a 6-month measurement campaign, right? So you got huge millions and millions of data points, and so you need good tools to analyze that, right? Customized tools for your analysis as well, in the main.
Yeah.
I mean, the community does work together and share tools, right? But they need to be good, right? Because you've got so much data to get through.
I know a number of data scientists, and inevitably they all end up being programmers and, you know, coders, because the stuff just doesn't exist to do what they want to do with the data, so they have to be able to do it themselves. So I've always been really impressed that these people that can look through this data are also writing stuff in order to be able to look at it in the way they want to look at it.
Yeah.
What about the hardware itself? Is the hardware pretty delicate and hard to maintain and complex, and like how is it a high maintenance thing trying to get good, because you know they say junk in, junk out. I mean, it's got to be all about the sensitivity and the calibratability of that stuff.
The real high performance instruments are these mass spectrometers. So lots of research groups would have those and are using those now routinely. I'm not saying it's straightforward, and it's still not straightforward, but we use them all the time. And we are getting better at developing and using the tools to get the most information out from the analysis, right? We also have on the other end, we have kind of routine analyzers. We have some sensors for all the pressure, temperature, humidity, CO2, whatever else. But we also have standard gas monitors for nitrogen oxides, ozone, SO2, and all that sort of stuff.
Yeah.
And the other thing that we do in UCC, my colleagues Andy Reef and Dean Venables do, they develop new measurement techniques to measure different atmospheric species. So looking at different ways to measure NO2, different ways to measure ammonia, and so on is a big focus. And also now we're also looking at radicals, to measure radicals using these more traditional spectroscopic techniques, but also using low-cost sensors, right? So we're trying to do a whole range of different things, and one of those is also improving the measurement techniques that we have available.
I was going to ask that because that was one of the outputs from this particular study, wasn't it? It was the looking at developing simpler, more low-cost ways of measuring what's going on with radicals, which it is not easy, I'd imagine.
No, it's not easy.
You certainly can't wheel around 500,000 pieces of equipment on trolleys around Cork city centre trying to mass spectrometry.
So here's the deal. The hydroxyl radical I mentioned before is crucially important. It drives the chemistry of the atmosphere, but we don't measure it.
Yeah.
Which is amazing, right? I mean, we can measure all the other stable gas molecules and everything else. Now, it is difficult, admittedly, and the equipment to do it is really complex, expensive, hard to use, and not transportable. It's, laser-induced fluorescence, or it's complicated mass spectrometers. It's very few research groups in the world do this. Okay, so it's not routine at all. And so the idea of our Radical project, which is an EU project, was to build a sensor. A very small sensor, just like an air quality sensor, but detecting radicals. And so this is a very ambitious project because, as you know, hydroxyl radicals are present at extremely low concentrations. They're very short-lived and very reactive. And so there's a lot of challenges there in being able to measure something like that, let alone a normal gas phase molecule like ozone.
A lot of cross-sensitivity is there in sensors for that kind of thing.
And exactly. And so this Radical project actually was a great project because it combined physicists, material scientists, atmospheric chemists, and we had some technology companies as well, all coming together, bringing their own individual expertise to design and test a sensor for radicals. And the idea was quite different. Rather than using light or a mass spectrum to measure the radicals, we were just using electrical detection. It's a very simple, straightforward, a silicon-based device that could be manufactured quite cheaply, but that would also have the sensitivity and hopefully the selectivity to measure radicals. We just come to the end of the project now, and we had some success. I think it was a big challenge, all right? I think if you were to sit any atmospheric scientist here today, they would say it would be almost impossible challenge. But we did get a measure of success. We certainly used the sensor to detect hydroxyl radicals. So we got pretty much real-world sensitivity. We were at the parts per trillion level sensitivity for hydroxyl. We didn't get the selectivity that we wanted, though. So there are interference effects from other gases like ozone and nitrogen dioxide and so on. And so we got so far, and I think that now naturally we're going to look to the next phase of this development to develop the sensor further to see if we can get that selectivity. Yeah.
Is so a solid first step anyway. I mean, in the sense that you learnt a lot about free radicals and hydroxyl radicals, and you got a sensor into the ballpark, shall we say.
Yeah.
So now it's about...
Well, we measured something, right?
Measured something.
And I was delighted when we managed to show that it's measuring hydroxyl
better than looking
radicals.
at a flat line on a screen going...
Yeah, no, I mean, because, I mean, if you've got no signal, that's it. You just got to work to... That's what I say to the guys in the lab, my students, my researchers, that... Just as long as you get a signal, then you got something to play with. You got the start, right? And you can play with it. And we did, and we got response from OH, which was really good. We got responses from other gases. And actually, there are potential side benefits from that, right? Because we think we can possibly take this as a platform. And with certain different types of coatings or manufacturing procedures, we might be able to tailor a device to be an ozone sensor, to be an NO2 sensor. all right, to be an ammonia or hydroxyl radical sensor. Now, that's,
you might have broken ground in trying to measure the impossible, but you've made what's already possible even better, perhaps.
Yeah.
So, because we've got ozone sensors and NOx sensors and so on, but this might be a better way of measuring them and more precise. You know, you're taking on a big challenge with the hydroxyl radicals.
And the real strength is the use of electrical detection as opposed to spectroscopy or mass spectrometry, which involves expensive equipment. Or if you just got electrical current, that's it. You can have a small device, right? You don't have to have all the fancy optics for spectroscopy or the spectrometer for mass spectrometry. You just got a little sensor, just like a portable or stick on the wall air quality sensor.
So the project's finished now. It's wound up?
The project has just come to its end, and we are at the stage there. We are looking at the next phase.
Yeah.
We have some ideas already, and so we are having continued discussions with consortia to work out exactly what are the next steps. But we have some ideas in train, and we're also actually just received news that with that type of platform, we've now got an opportunity to develop it for an ammonia sensor. So I think that as a group now, this collaboration between the material scientists who make these devices and the atmospheric scientists looking for the application, you know, we've actually, it's been quite fruitful.
Yeah, there's some good potential outputs from this stuff. That's always encouraging. Yeah.
Yeah.
How long a period of time was the project? Is it kind of like a?
This was a 4-year project.
Yeah.
And it was.
Who was it funded by? Was it
European funded, Horizon funded project? Research groups from Bulgaria, Germany, UK, Greece, Ireland, and different expertise brought from the different areas.
Yeah,
really helped make the difference there for sure.
Was there anything that surprised you in this study? That was something that you learned, what you didn't think
that it worked? No, I was very pleased that
what
it
you were
worked.
seeing with the chemistry, or even what you were seeing with the labs and the tests.
Well, the sensitivity I was surprised at.
Yeah.
Okay, because when we used this artificial source to generate the hydroxyl radicals in the lab at quite high concentrations, so they were elevated. I thought, we're seeing, parts per billion, not parts per trillion. But when we, moved the light source away, the radical source away a bit further, we were able to measure more realistic concentrations, more real-world concentrations. We were in the right range.
Yeah.
So that was a little bit surprising that we had the sensitivity. Sure, we could detect parts per billion of ozone, but can we detect parts per trillion? 1,000 times less of this very short-lived radical species, and we did.
And what about the co-benefits of all of that knowledge and equipment and resources that have been buried into, particularly here in UCC with the labs and what have you? Is there ongoing uses now for that chamber and the knowledge that you built in internally here to measuring this kind of stuff? So
there's ongoing collaboration, as I mentioned, that we're working on the next project now for an ammonia sensor. We're looking to carry on with the radical work, I think, at a European level with the European consortia. The chamber also is used by a variety of other projects. So we have a project called Atmotrace, where we're developing new spectroscopy techniques for different species as well. We're looking at emissions from agriculture. Okay, we're looking at emissions from slurry, and we're also looking at a whole range of other VOC chemistry. As I mentioned, these secondary organic aerosols are a very important topic. So we have a variety of projects ongoing which use the chamber facility as well.
And how do these lab projects like Radical then connect with your kind of field research and with general atmospheric chemistry and air pollution? Are you taking what you were learning from that and applying it to the other stuff that you're doing, which we'll come on to next, around ambient air pollution and things?
Yeah. Nearly always any new technique is always developed in the lab. And then you scale up, you go for, you just see if you can see something, and then you look for potential interferences, and then you test it under a range of different conditions. That controlled atmosphere is key to being able to do that. And then ultimately you go to the context of the real world. And so we haven't quite done that with the radical sensor, but we have done it with the other spectroscopy techniques that the guys in our group have done. So, for example, colleagues have taken some optical setup, used it to detect nitrogen dioxide, NO2, in the lab on the optical bench, like a laser bench, and then you use it in the chamber where you can control the conditions, and then you go out to the field. And I was chatting to a colleague earlier on today. He's going to go out tomorrow with this in a car. All right. And so they're trying to test this as a mobile sensor already. And so you do this gradual stepwise progression.
Yeah.
But you start from an empty laser bench. You start from an empty bench in the lab, and you build up in terms of the complexity.
Understand the fundamentals,
Yep.
Understand the principles, and just steadily apply it and scale it,
Right.
apply it and scale it, and so on.
And experiments in the chamber on this chemistry, the VOC chemistry, are really important, because if we're going to do some measurements in the lab, we might measure in the field, we might measure some stuff and go, where's that coming from? Okay, well, we're in an urban environment, there's lots of traffic nearby. Maybe it could come from benzene. Let's go and look at the reaction of benzene. Yes, benzene does produce this compound. Okay, so we know that benzene chemistry is occurring outside. And vice versa, we do some chemistry on, isoprene in the lab, and we say, oh, this is interesting, it produces these species. Do we see those in the field? Yes. Isoprene chemistry is going on in the field. And then the chemical processes that we study in the lab can be used to interpret the data in the field. And that's where you get more complex air quality modeling, looking at the impacts of emissions, different emission scenarios on secondary pollutant formation like ozone.
So this is where you start to get into what you're doing with the ambient air monitoring out there, where you're taking less complex data sets, but much, much bigger. And the chemistry that you're understanding in the lab are helping you develop the models and the formulas to understand what you're seeing at scale. Yeah. So you can get a sense of, why are we picking up and seeing this in this situation? And then when you see it appearing in the data, you've got a fundamental understanding of why it's there then. Yeah.
So we need this combined approach.
Yeah.
And also to bridge as well. They shouldn't work on their own. There should be connections. And we try and do that wherever possible.
I'll have you back in just a minute. I just want to borrow you briefly to talk to you about 21 Degrees, a partner of the podcast. Formerly the Green Building Store, they were founded in 1995 by 3 exceptional building professionals, and the company grew out of their frustration with the poor availability of ecological building products. And I've known them for years as the go-to company in the UK for end-to-end design-led MVHR systems. You see, your home should do far more than just provide shelter and be energy efficient. If designed correctly, it'll be a far healthier and more comfortable environment. So whether you just want to start with a single product solution or need a comprehensive range of technologies to make your home more comfortable, 21 Degrees can help. In 21 Degrees, you won't find a more trustworthy, straight-talking, passionate about what they do, and approachable group of people. I speak a lot about the performance gap on this podcast and what we can achieve if we value ventilation highly enough. 21 Degrees embodies that sentiment for me. So if you're building a home, looking to install ventilation, or need to talk to experts in the field, I can't recommend them highly enough. Links are in the show notes at airqualitymatters.net, and you can find them at 21degrees.com. That's 21degrees.com. Now, back to the podcast. No, it's a fascinating area, an area I don't think I've ever heard talked about before, free radicals and hydroxyl radicals. But it sounds like it's a fundamental engine room of a lot of what's going on.
Yeah.
Be interesting to see what the next step looks like. Do you know where are you out for funding? Have you formed an idea of what the next project looks like?
Yeah, we're working on it. We're just trying to identify the best call, because some of the funding programs are more directed towards faster technology development. There are still issues with some of the fundamental science, the exact mechanism, the sensing mechanism that we're trying to pin down. I think we want to do some more fundamental work before we are able to, I think, get this selectivity, because I think we will be able to get the selectivity, but we need to understand that fundamental sensing mechanism. What's going on when the hydroxyl radical hits the surface, interacts with the stuff on the surface, causes that electrical current to be generated. What's going on? And so we're trying to understand some of that with theoretical approaches as well as experimental work.
And as you were saying, at a global level, this stuff, it has the potential to impact the environment, atmospherics and global warming and all these kind of things. So understanding free radicals and their impacts on clouds and pollution and particle generation, and, you know, feeds into better models to understand and predict.
Yeah, I think if you can measure the radicals in the ambient environment, you've got an idea of what we call the oxidizing ability of the atmosphere. Right? If the OH radical concentration is low, then it's not going to be a very reactive atmosphere. If it's high, it's going to be a reactive atmosphere.
Yeah.
Okay. And so you've got that handle. We just don't have that information. You can, using chemistry models, do some predictions, and quite often those predictions are quite good. But we could certainly benefit from a lot more measurements. And you need an accessible, low-cost technique to do that.
Yeah.
Because not everybody has the ability to deploy this expensive kit to measure radicals.
From a pure chemistry perspective, have you been able to kind of theoretically run the numbers? Are there runaway scenarios like we get a lot with global warming of hitting certain benchmarks or points where we're creating so much of this stuff that there's unintended consequences of global warming or changes in the atmosphere? Is there some unintended chemistry potential downstream, do you think, at a climate change level?
I mean, we do see, as I said, this chemistry is natural chemistry, and it's enhanced when we just add more stuff to the air. So when we have these additional VOCs and nitrogen oxides from combustion processes and so on, then you do get this enhancement.
Yeah.
So the hydroxyl radical will react with whatever's in the air to make ozone. But once you add a lot more VOCs and NOx, then you get a lot more ozone formation, a lot more aerosol formation. And so we see that in specific environments, but the daily nature of the OH production and so on means that this is a cycle, more or less. As we go forward, are things likely to change? Maybe emissions, certainly from plants, are going to change with a warming climate. We're already seeing, I think, as a big concern, quite a hot topic at the moment, is wildfires. So the impact of wildfires on air quality. What about those emissions? There's a lot of black carbonaceous material going into the air, those particulates, but also there's a lot of volatile, semi-volatiles that go with them too, right? The stuff you're smelling is the volatile semi-volatiles. Okay, the stuff you're breathing in is all of it.
And that's so free lunch for radicals, I guess.
One thing that is changing is we're getting more wildfires. And so we're getting probably more event-based things, like typically you would get winter air pollution, summer air pollution events. But now we're also getting wildfire air pollution events. And these can be huge, right? I mean, they're the size of a continent, right? You know, so these are, we're in Ireland, the UK, we're in a part of the world where it's not a very big problem, but we do have some problems. There were wildfires just recently in Ireland, right? With and there will be in the summer. And when you go to southern Europe, it's a very big problem now. And of course, United States, Canada, Australia, and lots of other countries. So I do think the wildfire issue is leading to a change in our composition. And it's event-based, but if these events are going on at different times all around the world, then you are changing composition. And we're lucky. We don't have, where we are, we don't have events where we have to stay locked inside and turn on the air purifiers, right? The air filters. But there are in the USA, right? There are in other countries where people...
I don't know, and it's a fabulous segue, John, into my next segment, which is... there's periods of time, whereas I've been in Enniscorthy, where you probably need to shut the windows and turn the filter on.
Yes.
Because of particulate smoke and wood burning and peat burning and coal burning and what have you. So we still get pockets of very poor air quality in Ireland in certain atmospheric conditions, certain areas of the country can have very poor outcomes, can't they?
Yeah. And we've done research into this now for the last 10 to 15 years. We initially started in Cork City, and we were quite surprised to find that there was a lot of coal burning, peat burning, wood burning. So in the winter months, the particulate pollution is quite elevated. It's probably double on average the amount of pollution in the summer. So this is obviously a very seasonal effect, and it was evening. And then the chemical signature of the particulates showed that we had coal and peat and wood burning. And this is Cork City 15 years ago, where, by the way, there was already a ban on bituminous or smoky coal. And so we thought, wow, that's quite serious air pollution, which wasn't really thought about as being a big problem. And certainly at that time, people weren't looking very much at the composition. It's when you look at the composition of the particulates, can you say, oh yes, that chemical signature corresponds to wood burning. That chemical signature corresponds to peat or coal or traffic or so on. Okay, so different chemicals. So for example, sea spray would give you a sodium chloride signature. Wood burning would be identified by potassium, okay, because it's always present in living material and recently living material. You look at carbon, organic carbon. You look at some other fragments from breakdown of things like cellulose, lignin, all right, and you can work out these come from wood burning. And then you do your fingerprinting. Yep, we got coal, we got wood, we got peat. And so we said, if it's bad in Cork City, what's it like in places where there's no ban in place? And there are literally tens, if not 100 towns in Ireland that at that time didn't have a smoky coal ban, but because they were not on the gas grid, solid fuel burning was a regular nightly event, okay, just to heat the house. And we went to 3 small towns, Enniscorthy is one of them, and we measured the same, elevated pollution levels at night, really quite bad in some areas. Enniscorthy was the most polluted at the time, and we had this kind of winter smog, so it's like the London smog of days gone by, but present in small towns. And this problem we saw in many small towns across Ireland, and again it was all 3 solid fuels. It wasn't just coal, but it was peat and wood as well. And we saw all 3 solid fuels present in the emissions that we were measuring.
Yeah, and it and it's real. I mean, I live near Enniscorthy, and when you drive in on those winter evenings, there's a lot of sports pitches up on the hill in Enniscorthy. The GA pitch, the rugby pitch, the soccer pitches are all in a similar area, and they've all got big floodlights lit, and it looks like there's fog. It's very pronounced. You come in and you can taste it in the air. It's very, very prolific, and at multiple folds over the WHO limits for particulate matter at those times. So I think it's a very real thing.
Enniscorthy also is it's the set in the topography, and it's set in the valleys. So the combined with the the temperature inversion because of the winter months, nighttime, you also have the topography, which just kind of acts like a trap really for the pollution, right? And Enniscorthy is one of those towns that had a particular problem. But our research was acted upon. We fed all this information into the Department of the Environment, and it was used. I mean, for many years they were talking about a ban on smoky coal extended nationwide, and we said, great, but peat and wood also contribute, so we also need action. It's a solid fuel burning problem. It's not just a coal problem. And eventually, there was new solid fuel regulations brought into Ireland in 2022, which was a nationwide ban on smoky coal, but there's also no more large-scale extraction and selling of peat, and there's some measures on wood as well, in terms of the humidity. Wet wood is more pollutant than dry wood, and so on. So, look, those measures, actually, the timing was unfortunate because they were introduced at the time of the start of the Ukraine war and the cost of living crisis and everything else. So it was a bit difficult. But the latest news is that we've just finished a measurement campaign in Enniscorthy in a project called Town Air with colleagues from the University of Galway, and there's an improvement, right? So our first measurements in Enniscorthy were 10 years ago. And what we see is a good reduction in PM 2.5. We see less carbonaceous material. So over the time, the air quality in Enniscorthy has improved quite a bit. So obviously, hopefully, the regulations have played a role there. And the local authority as well, Wakefield County Council, has been quite active in promoting the use of cleaner ways to heat your home, right?
Yeah.
So I think that combined with the scientific information has hopefully had an impact.
Yeah, and particularly in these smoky old towns that you get, they're quite evocative in some ways, and in a strange more way. Even though I know how awful it is, there is something quite evocative about that smell when you come into an old town, smoky town. There's a smell of peat and coal in the air that is of a time gone era. It's a bit like when we've got a couple of steam engines around where I live, and when they go chuffing down the road, the amount of pollution that comes off these things is horrendous. Yeah. But there's a smell to it that smells of history. There's something about it that's quite strangely evocative at the same time of being
there is
awful.
And I think to an Irish person especially, of the smell of a good peat fire, because it's evocative, right? And furthermore, it's part of tradition. I mean, that was one of the issues here, I think, was that it's such a part of history, digging up peat and using it for your fuel. It's tradition, right? And part of culture in a way, especially the rural way of life. And so that was an issue that had to be dealt with, I think, in Ireland.
And to be fair, it's one of the few air quality events that you can actually see and taste. So it's not like this is an invisible problem.
Right.
Like, you're not speaking to the residents of Enniscorthy and they go, what air quality problem? I don't know. There's, anybody that lives anywhere near Enniscorthy knows in winter it's poor air.
The key thing about it is that you get these huge spikes in particulate pollution that are lasting 2 or 3 hours. Look, hundreds of microgram per meter cube. Hundreds, right? Almost like Delhi levels of air pollution. But they're only for those few hours. And when you take the annual average statistics for the whole year, it really isn't that high.
No.
All right, but you get these very highly polluted periods, cold winter evenings, where if you're elderly and you've got respiratory issues, or if you have maybe your child has asthma, you're thinking, right, I'm not going to sign up to soccer practice tonight, right? And so I think it was important to make that connection that it's not just compliance level annual average data. It's those little periods of time where people might be going out for a walk or doing something. And if you've got that information that you can share with them, they can make decisions that could affect their health, right? So I think that's really important to get information out there.
How much of a problem do you see with the ambient air monitoring you've been doing with traffic pollution in Ireland? Are there areas of the country where you're seeing significant levels of pollution, NOxes and soft oxide and particulate matters and so on?
The research that we do is focused on a field measurement campaign that's intensive with all of instrumentation for a season, maybe a year if we can. Okay, so for example, we went to Dublin Port and monitored for a year, looking at ship emissions and other emissions. Routine monitoring is carried out by the EPA, and in other countries, the environment agencies would do the same thing. They set up monitoring networks, typically run by the local authorities, measuring the typical pollutants like PM, nitrogen oxides, and ozone especially. And what we see is that PM levels are by far the highest in the winter, and by far during those cold winter nights. So it's very much, even without taking our fancy equipment to these places, you can say, right, 8 o'clock on a cold December night, that's going to be, solid fuel burning.
Yeah, this isn't people going out into their cars at 8 o'clock at night, sitting there warming up in the cars. This is,
in comparison, the little bump due to rush hour traffic is really quite a little bump. So direct particulate pollution from traffic is much, much less.
Yeah.
Now, there could be some secondary pollution from the processing of the emissions, that secondary organic aerosols I was talking about. But in many cities, it's the nitrogen dioxide problem. I think that is very much traffic related. Okay, so
one of the things I was surprised to learn from an air quality conference I was at last year was how much of a problem commercial kitchen pollution is in big urban centres.
Right.
So in London, just behind road traffic, the pollution is commercial kitchens for particulate matter and other pollutants, which was a complete surprise. I wouldn't have even thought of it, to be frank. But yet you go into the restaurant quarters in London and everybody knows that lovely smells. The barbecue smells, the cooking, all of that is pollution. And it's like a third or something of the PM pollution.
In certain areas, I remember being on a measurement campaign in Paris and we were near Chinatown.
Yeah.
And it was, again, a big thing. And
VOCs.
It's been identified. People have done research on this. It's called cooking organic aerosol.
Yeah.
All right. Because it contains different types of organic compounds.
And not nice ones either. You've got like polyaromatic hydrocarbons.
Or there are fatty acids and things like that. So these materials that are byproducts of food cooking that just condense into that kind of mist of particulates that you can see. And obviously the aromas that go with them as well, right? And so the phrase is cooking organic aerosol, and it can be significant in some areas.
Yeah.
So a lot of the things that we do, I mean, I know your indoor air quality is your hot topic. I mean, cooking does affect indoor air quality, but it can affect outdoor air quality too.
Yeah, for sure. Have you been pulled into indoor air quality much with what you do?
A little bit,
particularly with the particulate matters and the heating fuels, solid fuels, and things like that. Have you found yourself looking at indoor emissions of that as well as outdoor?
Yes, to some extent. I mean, we got involved more with indoor air research at the height of the pandemic, right? Was for different reasons. But I mean, the same sort of measurements that you can make outdoors, you can make indoors. And there is a huge level of interest in indoor air pollution, especially people that have wood stoves or fires in their home.
Yeah.
Okay. Now, we haven't done this research, but there are researchers in the UK that have showed that you get elevated PM levels, elevated particulate matter levels, you get elevated benzene, you get carbon monoxide, you get all the obvious combustion pollutants indoors to a much greater extent than somebody who doesn't have a fire or doesn't have a stove. So that is true. We are hoping to do some research soon. We put an application to do some monitoring in towns, outdoors, but also indoors. And the idea is to have some monitoring outdoors at fixed sensor locations, but also indoors, and also some mobile sensing. So we've got the whole lot.
Yeah.
Okay, so we do think that will provide a huge amount of valuable data. And we're hoping that some of this may be community driven as well, because we know that one of the best things you can do to improve, to get people, to raise awareness and get people thinking about their air quality and what they're doing, is to get them involved with the projects as well, right? So
absolutely.
I think that could be a nice way to go to a town and do a combination of that outdoor, indoor and mobile monitoring, bring in communities, and then everybody gets a buy-in and understands what they're doing, how they in their homes, and so on, might be affecting the air that everyone breathes.
Where's the gaps in ambient air pollution monitoring and research at the moment, do you think? I mean, I'm sure there's many, but in the sense that, is it the majority of it a policing issue at this stage of just networks of sensors, understanding patterns and events and drivers, or is there some kind of fundamental research still being done or trying to learn about air quality outside? What's getting people excited in that kind of broader ambient air monitoring space these days?
There is a lot of things, actually, and in terms of the composition of the particulates, I think that people are starting to look at some new metrics, okay? So the toxicity of the particulates. So people are not just saying how much PM, is like, what's in the PM and what is it doing to you?
Yeah, I get in trouble for this all the time, John, because I keep teasing people that particulate matters, just like TVOCs, it's almost a meaningless
Right.
value.
Yep.
And they'd argue, no, it isn't. I mean, there's some straight lines between the raw number of PMs and public health. And we often know where they come from, whereas TVOCs could literally be anything.
Yeah.
But in a strange kind of way, it is the same thing. You know, we're talking about PM as if it's a thing, but it is different sources, different toxicities, different, like it's a complex beast of its own right.
But it's the same way when you look at food, right?
Yeah.
PM, you could say it's just the same as calories, okay?
Yeah.
But then you divide the PM into different components, all right? Like, I don't know, carbonaceous material, ammonia, and sulfate, nitrate, organics, chloride, whatever. And then you divide the food into salts, sugars, carbohydrates, fats, whatever.
Yeah, it's a great analogy, actually.
Right?
Yeah.
So then you can say, right, I want that information. I don't just want calories. I want to know how much fat is in there.
Yeah.
I don't just want PM. I want to know how much toxic polycyclic aromatic hydrocarbons are in there. I want to know how much nickel is in there. I want to know how much bad stuff is in and how much good stuff is in there. Or, you know.
Yeah, how much of it's sea salt, you know, yeah.
So just that one parameter isn't sufficient, okay, in many cases. It's fine as a metric for comparison with other places and looking at trends and everything else. But for its impact, you've got to break it down.
And where's the technology for that? I mean, at the moment, we're now getting pretty comfortable with optical particle sensors at scale. We're fairly happy with the numbers, the consistency of the numbers that we're getting now at scale with these things. But that's a completely different ball game to speciating particulate matters. Like on the ground, what's the practical ways that this is being done now? And is there some development potential? Are we finding cheaper ways of speciating particles?
So to close off on the speciation, that is important for toxicity. This oxidative potential is now in the EU Air Quality Directive, the new EU Air Quality Directive. Okay. And so this is an important metric that we will be coming across a lot more of the next 10 years for sure. Okay.
Okay. So say that again to me, John. In the EU directive, the oxidative,
the term oxidative potential.
Oxidative potential.
So it is the ability of the particulates to cause oxidative stress in the body.
Right. Okay.
Their potential to cause oxidative stress is a measure of their toxicity.
Interesting.
To humans.
And that's measurable in a different way to speciating it, is it?
Yeah, there's a combination of toxicology measurements and so on. So it does start to become multidisciplinary, right?
Yeah.
But you do need high grade research level instrumentation to get that chemical breakdown.
Yes.
And then there's some assays, some ways to measure this oxidative potential. But now in the new EU Air Quality Directive, there's also black carbon, soot, if you like. There's also ammonia, and also particle number and size distribution. So there's a broader recognition now of just not what we've become familiar with, PM, NOx, ozone. It's all the other stuff as well. And so we're now starting to see not all measurement sites are going to have these things, but certainly some information in each area, would be important. Okay.
Yes, you might have one main site doing the more complex measurements and a series of satellite sites doing more basic ones, but building a picture.
A super site.
Yeah.
And so this is the phrase that's used. Super site.
Sorry.
So then there are a number of those in the UK. We're hoping to get one established in Ireland, but there are quite a few places in Europe, especially in America now, that would have these air quality super sites where you're measuring everything.
Yeah.
Right. Now you can't have those everywhere because they're highly instrumentated, very expensive to maintain, complex data sets, everything else. But they're starting to give us new information.
Yeah,
right?
Sure. And help us with the context of what we're seeing with the lower grade sites, basically.
Right, exactly.
Yeah.
On the other side of things, on a more real world level, one of the things that we've been quite keen to look into is the use of low cost sensors. Okay, and we've been experimenting with these for the last few years now, and seeing how good they are and how they can best be used. Right, and in summary, we see that the PM low cost sensors now are really pretty good for outdoor ambient air quality. We find that if we co-locate them with a reference instrument, a €50,000 instrument that is approved, certified, we get, in the main, excellent correlation for PM 2.5.
Yeah.
PM10 is a slightly different story, but for PM 2.5. And then we can get correction factors. You can make them more robust with temperature, humidity corrections. But in the main, you get a good indicative value for a low-cost PM sensor. And the value then is that you can deploy these sensors all around the town. And so we've been looking at that where we deploy a bunch of sensors together for about a month, look at how they'll vary. Almost all of them agree extremely well. We might kick the odd one out for not being very good, and then we locate them around the town. And now, around a town or a city, we get an idea of the variation in particulate matter.
Yeah.
And so
that might be topography, direction of streets,
the type of environment,
all sorts of things.
So we've seen, for example, if you deploy them in residential areas, in winter months, you get these peaks in the winter solid fuel burning, right? And so on. So you can identify these hotspots, and you can interrogate them, and you can compare them to each other. So the data is comparable.
Yes.
That's the good thing is, rather than having, one monitoring site in a town, if you have 15 sensors giving you information that are comparable, you've got that depth of information to answer specific questions. Which are the pollution hotspots in town? And then how can we use that data?
And the big data can unpack the sources just by timings and patterns and so on. Like sometimes, like you say, it doesn't take a genius to figure out at 8 o'clock on a December cold evening when you see a spike in PMs, you could bet your house on what is driving that particulate level. Unless somebody's lit a dumpster fire under that particular particle counter, like there's a good chance you're going to see smoky fuels driving a lot of that. Right, or at 9 o'clock on a Monday morning in the centre of town,
right,
and so on and so forth.
And we're also using some statistical approaches to do that as well. Okay, so we are looking at a fluctuation in a signal, a very high frequency signal. For example, in a smoke emission that might have a lot of variation, whereas you've got a slow moving regional air mass, that the pollution level doesn't really change, right? So we can separate out local from regional pollution.
Yeah.
And that's one of the things that we can do already, we think, with these low-cost sensors. And you can also get an assessment of the representativeness of the designated monitoring station. If the Environment Agency says, we're measuring here, obviously they would do their best to choose the site according to requirements. But how do you know it? How does it compare to where I live? How does it compare over here and here and here? If you do the measurements, then you got that information. Yeah. And so you got an idea of the representativeness of these locations. So I think there's lots of value for these sensor networks if the data is used in a good way to generate supplementary information.
Yeah,
it's not compliant, but it adds to the picture.
You think that's where the potential's locked in at the moment, is that potential to create value with low-cost sensors at a larger scale to make the invisible visible, engage.
It does raise awareness.
Public, raise awareness.
Because if somebody finds out they got a sensor in the neighbourhood, they might pay more attention to it, and then they say, "Here's the data. Look, your area is actually 2 or 3 times worse than the main street." What do you think is more polluted? Do you think the main road is more polluted, or do you think your housing estate is more polluted?
Yeah. And you just don't know where that data is going to be used as well. I mean, I work a lot with social housing in the UK, and there's a proliferation of indoor environmental sensors going into social housing, right? And most of the big organisations that do that technology are leveraging outdoor weather stations to supplement what they're seeing indoors. Right. So we're tying in data sets left, right and centre that are creating these not only big picture, regional, town level scale insights, but they're being used to leverage insights at a case study, homeowner, my bedroom level as well. Am I seeing high particulate level in my bedroom because of something I'm doing in my bedroom, or is it the fact that there's high particulate matter outside at the moment and I'm bringing it in, right? Yeah. So it's fascinating to see all of this stuff intertwine and where it's going to go.
I think so. And there's also some exciting developments in the use of low-cost PM sensors, possibly with some of the gas measurements as well, for what we call source apportionments. You know, that really complex chemical breakdown I'm talking about, how we can use the chemical breakdown to say we have 20% from traffic, 20% from coal burning, 10% from wood, 15% from peat. We can use low-cost sensors if we're looking at the time dependence and we're looking at maybe some other measurements, some other information as well as like habitual behaviour indoors or so on. We can actually use these low-cost measurements to look at the contribution of different sources.
Yes.
To the observed measurements.
And that's where your fundamentals on the air chemistry then come into play, because it's that information that feeds those models that go, these patterns are, because of the likely sources, are going to be creating this chemistry. And therefore, these are the likely outcomes that we're going to be seeing. So actually, rather than particulate matter causing a spike in asthma emissions, it might be the chemistry of X that's exacerbating asthma, actually. So it's this source we need to try and get rid of.
We had a great workshop here as part of the Aico project, and it was bringing together people that were looking at the sensor world, you know, the electronic noses, VOC sensors, just ambient air quality sensors, the people that were doing the complex chemistry in the lab, in the field to measure radicals, the people developing new spectroscopy techniques, and also our radical project all come together. And we what do we need to measure? And so the VOCs is certainly one area that we need to work out, because, as you see, total VOC, even if it is or not total VOC, right, you just get a signal, right? If we can get some VOC measurements nailed down, some specific molecules, even a very good total VOC, that would be great. And certainly linking some of those things, not just PM and not just total VOC, but some individual components would be very, very valuable, right?
Yeah, no, and you know, there's some really great work being done internationally on creating harm indexes for these pollutants. So whilst we understand how much of this is around and we understand its toxicological and epidemiological impact at a society level, a lot of the work like Ben Jones and Max Sherman have been doing around Annex 86 at the moment is this kind of total harm, this formula for figuring out what's actually causing us harm, what do we need to worry about and what we don't. And, you know, their best guess at the moment from the available research is particulate matter is accounting for about 75% of all the harm at a population level, followed by NOx and formaldehyde and ozone and radon in homes like ours. So actually, the limonene or the pionine, while it might be present at an epidemiological level or a toxicological level, might be a little bit lower down the list. Actually, if we concentrate on the PMs, the formaldehydes, the nitrogen dioxides, we'll deal with about 90% of the harm, according to the research. But the challenge is obviously that this is not speciated, so we don't know if that 75% of the harm we're getting from PM, where's that harm coming from? You know, so that all that's really fascinating.
Fares it from outside, I'm guessing, right? But
yeah, I think best guess is about 50% the particulate matter inside is from outside, roughly.
Right.
As a rule of thumb. And we know rules of thumb is always a good idea. And it'd be really interesting to see how that goes. The other thing I wanted to chat to you before we go is, I mean, we first got to know each other as we were banged together in the pandemic as part of the response in Ireland by government to bring in multidisciplines from different areas. And you and I and a bunch of others sat on the equivalent of Kath Noakes's version in the UK as in the Ventilation Advisory Group. And you chaired that. So you had the pleasure, I'm sure, of herding cats or trying to respond to questions. And I'm just interested because I had Kath on as well, and there were a couple of kind of reflective questions kind of 4 or 5 years on,
Yeah.
what your experience of that was as an atmospheric chemist and someone that understands air and science being pulled into a national emergency, and the kind of questions and responses that you were getting, when you look back on that period now, what your kind of reflective thoughts on it were.
Wow.
Yeah.
I think, like a lot of people, try not to go back there too often, right? Well, reflections. I have memories of just being so disappointed, I suppose, that there wasn't greater recognition of this airborne transmission route, right? Given all we know about aerosol physics and everything else, and the evidence that was rapidly coming to the fore, and the rebuttal of that from government advisors, not just in Ireland but around the world, really. I mean, that whole community kind of stuck together and wouldn't let the air quality or aerosol scientists in. So I think that on reflection, what needs to happen is we need to have a broader approach to understanding things like virus transmission and how it can be dealt with, how it can be mitigated and everything else. Because in the end, we know very well that, okay, the medics might be best placed to understand the virus when it's in the body, but when it's out in the air, that's the domain of physics. And the way to treat that is the engineers' expertise in managing air and everything else.
Yeah.
And so the whole response was very much medically centred, certainly in Ireland, I think initially in the UK, and generally around the world. And so, I mean, we were quite vocal about gaining better recognition of the importance of airborne transmission. We got somewhere in the end, but probably it's not had the lasting impact, I don't think. I think there was some acceptance at the time. But as far as I'm aware, the whole droplet aerosol definition is still, not resolved. I mean, I don't know how far it's come on. Certainly amongst practitioners in healthcare and everything else, I don't think they have any improved understanding. So I think there are still knowledge gaps. I'm not saying people have gone back to exactly the way they were. I mean, people will always remember the masks and everything else. But I'm a bit disappointed that there hasn't been an impact. It's certainly in healthcare, right, in hospitals and so on.
Yeah, I asked Kath that question, and her kind of overwhelming feeling was we were asked quite complex questions in that period, but actually her overwhelming sense was a recognition of just how little we knew about the performance of the buildings that we own and occupy. That at a that a lot of the challenges that we had were having to explain the basics of ventilation, explain the basics of air quality monitoring, explain the basics of hierarchies of control. It seemed that there was just this fundamental disconnect somehow, was kind of her overwhelming kind of reflection on it. That, I think people will argue eternally about the R value risk in a Wells-Riley model on whether how likely you are to be infected. As Ben Jones puts it, we now know with 100% certainty that your chance of infection is somewhere between 0 and 100%. So, I think that argument will roll on. But what we definitely know, from my perspective, having come out of that pandemic, is we have absolutely no idea of how our buildings perform. We've had a code of practice for indoor air quality in the workplace that was launched 3 years ago. I haven't heard a whisper from the Health and Safety Authority. I launched my consultancy at about the same time as the code of practice went live. And I've got a page about indoor air quality in the workplace, and I'm very well placed to help people do that. I have had 0 inquiries about it. Not a person even knows about it. For me, I think similar feeling to you. I just feel like we've come out of it, and for the vast majority of the built environment, we'd rather just forget it ever happened and probably not invest any money next time round.
I mean, certainly in high-level meetings that I was in, there was big concerns about the cost. All right, about the cost of implementing change to, I don't know, renovating buildings, overhaul of ventilation systems, additional monitoring, upgrading of facilities, the whole lot, which would go into billions, right, without doubt.
Well, I just remember the conversations we had over classrooms and schools. I mean, the fear of having to recognise that somehow we might need to do something substantive with classrooms filled the OE with horror.
And, I mean, just to stick with that, I mean, at least it was better. The interaction with the Department of Education, for example, and also my own experience with the Department of Agriculture, they were much more willing to take on our advice and act. You know? I mean, in Ireland, we were one of the first countries, I think, to have CO2 monitors placed in schools and that robust ventilation guidance. But that was done with the Department of Education. I mean, they took our documents and guidance and they tailored that to their specific needs. Now, implementation wasn't perfect and was a bit difficult because there's literally thousands and thousands of individual classrooms and lots of things depend upon the action of the teacher and everything else. But, you know, I mean, I do think that, you know, it did raise awareness. It did make people think about the air because, I mean, people don't think about the air they breathe at all, right? It just happens. We breathe 11,000 litres of air a day. We only drink 2 litres of water, right? And you wouldn't think, you can see dirty water. You can't necessarily see dirty air. These whole things that we keep on coming back to make air quality visible. So in the end, you are right. When you build buildings with certain specifications, you need to monitor that. You need to monitor their performance. So I do think that's crucial. And that is one lesson we should learn and fix, right? I mean, we should fix that problem. I mean, I agree with you completely, especially in higher risk environments like healthcare. Classrooms, because of their small size and large numbers of kids crammed into them, right? Other places like public transport. I mean, I'm sitting on buses or planes. There should be more monitoring. There should be more information.
Yeah, and here's an interesting conversation I've had recently on the podcast with a lady called Victoria Plum. She's based in Australia. She runs something called the Safer Air Project.
Right.
And she comes at this from an accessibility rights perspective. She along with her family, have suffered with long COVID. Her husband's got a condition that makes him vulnerable anyway, a kidney condition, I think it is. And she's found herself advocating for people that are vulnerable to indoor environments.
Yeah.
And there are many people, anybody that's under cancer treatment, that it's affecting their autoimmune ability, the people with particular conditions, long COVID and so on, COPD, the whole bunch of people that are effectively excluded from spaces because of the risk of the air quality in those spaces. And actually it's an accessibility rights issue in the same way it is for wheelchair access or hearing impaired or visibility impaired people. And I found that a fascinating angle because we actually have a lot of the levers and the legislation in place to protect people from right of access, right, because of disabilities. So often a lot of the fundamental law is already there. And actually it's an issue of fairness. And I think society responds quite well in general to fairness. If they feel that people are excluded in an unfair way from spaces, they'll move heaven and earth to fix that. And we see that, if a child has a disability, a school generally move heaven and earth to make sure that classroom's accessible for them, right? Or has some hearing aids to help them participate properly in the school. But there are kids who are having to wear a mask in a classroom even today because they don't want to go home and kill daddy. Or as she puts it, her son, that when there's a school trip, she has to drive him separately, can't go on the school bus.
Yeah.
Because it's an accessibility challenge to them as a family. And I find that a fascinating perspective to look at the spaces that we operate and own, that actually there's a fundamental, we should be making public spaces
I agree.
accessible.
There were several journalists in Ireland that were really promoting this aspect. That we, well, I was going to say thrown these people under the bus, but there are people.
Quite literally, yeah.
There are people who could die from just getting a COVID infection, right? They got an autoimmune problem. They can't get the vaccine, right? If they get a COVID infection, they literally could die or have long COVID, which it's, from all I've heard, sounds pretty desperately bad. And we should be, I mean, in some cases, it's just very simple measures. A school takes responsibility to say, look, in the classrooms, we're going to do what we can for you.
Yeah.
We're going to improve ventilation, and we're going to have some air filters in the classrooms. And these are not expensive things to do.
No, and full of co-benefits. You know, it's like,
Well,
yeah.
that's it. I mean, oh, by the way, the other kids in the class who suffer from hay fever will benefit from these in the summer as well.
Probably get some better test scores. There'll be less sickness from the
Performance
teachers.
benefits
You'll
in the
get
classroom.
big absenteeism from teachers and school. You know, like there's all these, a bit like wheelchair ramps, provide access to the bank for the person in the wheelchair, but they also make it a lot easier for the mum with the pushchair.
Yep.
Like it's an obvious co-benefit, and like so that there's all these co-benefits that come with it as well. So I find it a fascinating way of looking at that challenge. Is it actually enables us to pick buildings off one by one and introduce legislation that says, by the way, if you have a building that's open to the public, you either need a safe floor or a safe room or a safe space that the people that are likely to be vulnerable can access without fear. You're not going to eliminate the risk. You never will, but you'll be able to reduce it for them.
Yep.
And give people a chance. Because as she points it out, like in the UK, they were living in the UK at the time, Boris Johnson declared Freedom Day. And she said that's stuck in their throat enough that they ended up moving.
It's not their freedom.
It's actually got worse for them because kids were allowed to go back to school infected.
Yeah.
So actually it made the world more risky for a lot of people if you're vulnerable. And the other interesting thing about being vulnerable is that very few of us can sit here and think there's a very good chance that 1 in 4 of us are going to be in a wheelchair, right? Or lose our sight meaningfully. But we already know that 1 in 3 of us, 1 in 4 of us are probably going to get cancer or some long-term illness that, due to the medication that we're on, is going to make us vulnerable to air quality. So actually, that vulnerability could be any of us. Much more so than a lot of other accessibility right conditions. So it should matter to everybody as well. This is a very real thing that affects real people.
Plus, at any one time, we will know somebody ourselves, family member, friend, that is vulnerable or has vulnerable family members. So I do think there would be buy-in if it was pushed forward, promoted. But I mean, it's difficult. I don't know how they bring it forward, but I think keep on fighting. I mean, we saw the success eventually in the UK with Ella's case.
Yep.
You know, the famous case.
Roberts, Ella, Chrissy, Deborah. Yeah,
exactly. And so I do think in the end, once you get a level of recognition, then you will get some impact. But it is disappointing. I thought one of the little wins that we had from our efforts during the height of the pandemic was this new code of practice for indoor air quality. And it's not a bad document.
No, it's pretty good.
It's really good, right? But the problem is all about the implementation. Whether there's the will to implement it from the government, from the HSA, the Health and Safety Authority. There's not enough promotion, raising awareness about it. And there's a whole education piece that needs to be done.
Yeah.
So I think, as you said earlier on, we've learned the extent to which we don't know things. And whilst we may know, the general population doesn't.
No.
Right? And I do think that we have an education piece to do still, because I fear that already years have gone by where there's still no update to pandemic planning, right? To what extent is any airborne transmission built into pandemic planning? To what extent are we future-proofing our buildings, our society, the health of our people against an airborne disease, right?
Yep. No, absolutely. And no sense that we've lent on any awareness that was built at the time and built on top of that gone, hang on a minute, there was an opportunity. We've had an opportunity where people were suddenly aware that the air could present a risk, and we've not been able to build on that effectively, which I think is a lost opportunity somehow. But like you say, there were some successes of that group, and I think if nothing else, it enabled a multidisciplinary team of engineers and abstract scientists and public health people to come together. One of the interesting things I was going to say, actually, the work that they've been doing with the harm risk, the total harm index for indoor air quality, has been able to put a DALI on it, a disability adjusted life year metric on it, which is very useful at a policy level to understand the level of investment needed compared to the risk at a population level. And what they've been able to show is that the disability adjusted life years for exposure to indoor air quality is equivalent to smoking and twice as harmful as road traffic pollution and alcoholism. So it's at a level based on the harm that it causes at a society level that it should have investment. It should at least have comparable public health campaigns like we see with road traffic accidents and road safety about improving indoor air quality.
But to what extent do you see that governments or government departments see this is just too big a problem to deal with? I mean, is that an issue?
Well, it's never too big a problem to deal with if it has a big enough DALI impact, I suppose. You know, smoking was a really big problem to take on, right? But we recognised that it causes about 2,500 years lost to early death and disability per 100,000 of the population. That's understood to be plainly unacceptable. So you direct funds. You don't want to fix it overnight, but you start to implement rules and regulations and awareness campaigns and multidisciplinary teams to look at the problem, start fixing it. Similarly with road traffic deaths, you know, there's always that question of how much more wear do you need? Where's the baseline of just you're going to get per 100,000 of the population deaths? But it's understood that at about 12,000 years lost per 100,000 of the population, that's somehow unacceptable. So we put a good amount of funding into fixing it because it's real people's lives that are being affected. Yet indoor air quality sits at about 2,200, 2,300 currently. So it should be intolerable. It should be receiving funding.
It's also the same with outdoor air pollution. I mean, this figure's thrown around in Ireland, 1,400 premature deaths every year.
Yeah.
That's 6 times the amount of road deaths per year, right? So
we're talking the same kind of numbers.
There's a road safety authority. Why isn't there an air pollution reducing authority?
What air policies are, whatever, and so on. Yeah, for sure.
So it isn't taken seriously enough, I suppose, by government departments and agencies. And I do think that we need to get better buy-in from politicians. I mean, things can come up from ground level, but you can only get so far. We tried that a lot during COVID. I'm just thinking about what we did, and we were, prominent. We were in the radio and the newspapers or wherever else, and we were speaking to high-level government officials. And in the end, we had some impact, but not necessarily the impact that we wanted, right?
No.
And the lasting impact is minimal.
Yeah.
Right?
And you can see you see how delicate a thread this all hangs from. We see what's happening in science in the States at the moment, defunding of institutions, defunding of research, and this stuff can evaporate like the smoke in the air. So when we get these chances to build momentum, we really have to seize them. because it can so quickly, like we say, 5 years on, sometimes you wonder if it ever happened at all when you look around you, don't you, on the street and in there and so on. Yeah, really interesting. John, listen, it's been brilliant chatting to you, as it always is.
Yeah.
Thanks so much for the time, and thanks for arranging such a fabulous podcast studio.
Yeah.
Where are we today? Just for listeners that are looking at this on video, what's the name of this?
So this is the Aula Maxima, which means Great Hall. It's the original big hall in University College Cork, built in 1845. And so this is the big hall for functions in university, ceremonies, award-giving ceremonies, presentations, and it's a great place to be.
No, absolutely. Thanks a million, John. Appreciate it.
You're welcome.
Thanks for listening. Before you go, can I ask a favour? If you enjoyed the podcast and know somebody else who might be interested, do spread the word and let's keep building this community. This podcast was brought to you in partnership with Aereco, Aico, Ultra Protect, InBiot and 21 Degrees, all great companies who share the vision of the podcast and aren't here by accident. Your support of them helps them support this show. Do check them out in the links and in the show notes and at airqualitymatters.net. And don't forget to check out the YouTube channel by the same name, with plenty more content due to come on that channel. Thanks very much. See you next week.